PO, which stands for Performance Observability, is a product specifically designed to clarify the performance of AI applications, especially learning and inference processing. As you can see here, PO continuously collects metrics such as how much the GPU is being used, memory usage, network activity, and storage performance over time. You can freely move back and forth through this data to easily identify program bottlenecks and what was slow, allowing you to easily find such issues. This is a case where we used 2 nodes, each equipped with 8 H100s, to perform continuous pre-training and AI learning process. We're currently focusing on one of the nodes in a distributed setup. At the top, you have 2 GPUs and the CPU utilization. This is a fairly large system with about 240 cores. You can see the utilization is very high in the first half, and then it goes down here, which is when it finished. The GPU usage is more pronounced. The GPU is almost at 100% utilization, while the CPU side is around 50 to 60%. Of course, AI processing isn't solely done by the GPU. The CPU is doing a lot of work loading data, pre-processing, and initiating communications. Ideally, this CPU usage should also be pegged at 100%, but in this state, for example, we can focus on this little dip here and investigate what's happening. In this time frame, roughly around 40 seconds, there's a noticeable drop. We can examine what's occurring there by looking at other metrics. Of course, looking at metrics isn't anything particularly special. What's somewhat unique about this product is that it provides deeper insights, what's generally called a profile, that is, information down to the application's internals, the code itself. We aim to collect information all the way down to which parts of the code were slow. This is what's called a flame graph. As you can see here, it says total, and all the units are percentages. The horizontal axis represents the percentage, and the total is 100%. This visualizes what kind of program processing is happening during the focused time frame, which is currently about 40 seconds. The top is 100%. For example, this section labeled Apply here accounts for about 40% of this 40-second period. About 40% of the time is spent in the Apply section. The remaining portion, probably a little over 10%, is communication, the communicate function. Inside, it seems to be performing some kind of communication process. This corresponds to the source code, so people familiar with the code can gain even deeper insights. For example, AI applications are often written in Python, but underneath, they call highly tuned NVIDIA libraries written in C or C++. This allows for interpretation across different languages. For instance, if we focus a bit on this GEMM, which is matrix-matrix multiplication, you see the Python function gem is being called, but underneath it's using another optimized library, not the Python implementation of PyTorch, but a high-speed implementation written in C++. Going further down, we see CUDA calls. You can get a sense of roughly what percentage of time is being spent where. Let's look at a slightly different example. This isn't continuous pre-training, but an example of fine-tuning on a single node. This is when we performed fine-tuning using NVIDIA's official NeMo framework, or rather, model library. Here, the GPU fluctuations are even more pronounced than before. You can see that the GPU isn't being used very effectively. Normally, if someone were to analyze using NVIDIA SMI or something, they could see the instantaneous values, but they can't continuously monitor over the past few hours. By collecting information in this way and reviewing it later, you can quantitatively determine how effective it was. An interesting example is this storage write bandwidth, where you can see several peaks. If we focus on this and compare it to the flame graph, distinctive features become apparent. Looking at it broadly, there's save checkpoint on the left. It seems that at this point, after reaching a certain step in the model training, it writes out the model. This is to allow you to resume if there is a problem in the training program. This process seems to be related to checkpoints. It looks like the storage write portion is taking time because the checkpoint file is very large. The CPU is pegged at 100%. We might expect, for example, 256 megabytes per second, but we think the storage could do more. In such cases, Perhaps there's a bottleneck somewhere in the CPU's checkpoint processing. By looking at the metrics, examining the program's internals, and moving back and forth in time, you can perform various analyses. In a sense, you can interactively view these metrics and the program's internals along a timeline, jumping to different points. That's what the PO product is all about.